Okay, so what you should observe first is this whole expression e to the parentheses 2x plus y is equivalent to e to the 2x times e to the y. I hope you knew that, right? So as far as partial with respect to x is concerned, if you're trying to differentiate this with respect to x, this whole thing is a constant. Okay, so what does e to the 2x become? It becomes 2 times e to the 2x and then times e to the y, that is like a constant, okay? And so that stays. And then plus, then you take the derivative of this with respect to x, that becomes 2x e to the y, right? And so you can, if you like, you can put this together to e to the 2x plus y plus 2ex e to the y. That's okay. You don't have to simplify any further than that, right? How about fy? Okay, this may be a little tricky, but again, you take the derivative of this with respect to y. Well, e to the 2x is a big constant. It doesn't look like a constant, but you treat it like a constant with respect to with respect to y. And then e to the y, just if you differentiate e to the y, you just get e to the y, right? And then plus, what's the derivative of this with respect to y? Remember, x squared is simply like a constant. E to the y becomes e to the y. So what happened? Well, nothing actually changed in this, right? The partial derivative of fy happens to be the partial of f with respect to y looks exactly like itself, the function f, and that didn't change. And sometimes that happens, because of the way we differentiate this. All right, this leads us to, of course, the next thing, which is higher order derivatives. Okay, you could just guess what that is. Okay, so fx, that's the derivative with respect to x. You can take another x. All right, so what is that? This is the partial. Oh, by the way, this partial divided by or over f, the partial of x, this is called the derivative operator, the partial derivative operator. That means whatever comes here, whatever the function here is, you take the derivative of this thing with respect to x, right? So because fxx is the derivative of f of x, we denote it this way, okay? So remember, you have f first. If you take the partial of, if you take the partial of f with respect to x, this is what you get. And if you do it again, this is what you get. And so that's exactly what this is, all right? And so you can write this as partial square f, and you have a partial x squared. I know this sounds really weird, and by the way, you may remember the first derivative is written this way. The second derivative, if you remember, is written this way. And many of you may have thought this was a typo on your in your calculus book. I certainly did. It said, this just doesn't make sense. Why is this 2 between the d and y and this 2 after the x? Well, the reason is because d dx, okay, this is called the differential operator. This is the function. And so you can, I guess this makes sense, right? You don't really have to spend too much time thinking about this. But the reason this 2 is here is because this whole thing is called the differential operator. All right, whatever it is, it's the second derivative with respect to x, okay? And similar, f of y is the partial with respect to y of the partial of f with respect to y. So you could also denote this as partial square f partial y square. Okay, you may have noticed that I'm missing 2 things, okay, because I'm taking the derivative and then second derivative, right? The second derivative is actually the derivative of the first derivative. So what's the problem? Well, nothing, okay, but you could actually do this. What is that? It's the partial, and how do you read this, right? Well, it's f of x, y if you read it from the left, and you should, because that's how our language works, unless you read like Semitic language like Arabic or Hebrew or something. But f sub xy, this is fx and then we take that and take the derivative of fx with respect to y, we write this. So what am I doing here? You take the partial of f with respect to x, and we take the partial of this with respect to y, right? So if you write in the partial derivative operator notation, unfortunately, it's going to look like this. Well, that's terrible, right? Because now the partial y comes before x, and then you start losing like your mind, like, hey, am I supposed to do x first or y first? Okay, so typically we don't really use this notation very much. Try to stick to this notation because we are going to just keep reading from left to right. All right, similar. These are, by the way, called mixed partials. Okay, mixed second partials. F of xy, f of yx is the what's f of yx? Okay, that is the partial derivative of fy with respect to x. So you can write this as partial of f with respect to x of partial f, partial y. And so you could write it this way. But again, it's really confusing because this time now you're going to have to do y first and x next. This is because somebody messed up in history of mathematical notation, where somehow you have to read backwards when you write the function notation. Yeah, somebody goofed, and we can never go back to history because the convention has been established. So avoid using this. Use this notation here. So it looks like we have 4 different ones, right? All right. Let me give you an example. What is f x y? And this is a simple example. Maybe I should make this a little more complicated one. Yeah, I think I will. X y cubed plus sine of 2x plus y. Okay, is that complicated enough? Maybe not. All right, so let's find the 4 different second derivatives, the 4 second partials. In order to do that, of course, I have to find the 2 first derivatives, right? So f sub x, what is that? That's y cubed. Remember, because this part is just like, y cubed is like a constant. So this is y cubed plus, what's the next one here? It's going to be cosine of 2x plus y times the derivative of the inside function with respect to x, which is only 2, right? What happens to y? Well, y is like a constant, so you don't have to worry about this. F sub y, okay, so this will be, x, which is a constant as far as y is concerned. Y cubed becomes 3y squared. Get that? And then this one will be cosine of 2x plus y times the derivative of the inside function with respect to y, but that's just 1. Okay, so you don't even have to write that. Erase it. Okay, so that's those are the 2 partial derivatives. Now, let's go to the second partials. Remember, you have 4 of them. Oh, by the way, if you go to the third partials, then you will have 8 of them. The fourth partials, you have 16 of them, because you have to permutate between x's and y's and so on. Well, it turns out you don't have that many, okay? And I'll explain why right after this. But what is fxx? Yeah, maybe you can try all of these and then figure out what they are. You will have 4, the second derivatives, right? Fxx is the derivative of this with respect to x, okay? So now you have 2, and then of course cosine will give you negative sine of this, and then you multiply that by the derivative of the inside function with respect to x, so you have another 2. So this is negative 4 sine of 2x plus y, and y cubed just completely disappears. I hope you know that. Fyy would be the derivative of this with respect to y, so you get 6xy, and then minus sine of 2x minus y, right? Because you have cosine of something, so it becomes negative sine of that, times the derivative of the inside function with respect to y, but that's also 1, so this is it, okay? All right, how about fxy? This one is a little different because now we take this derivative and differentiate that with respect to y, so 3y squared is what you get first. And then now you have minus 2 sine 2x plus y times the derivative of the inside function with respect to y, which is 1. So this stays. All right, finally, fyx. So this time I'm going to take that function, f sub y, and differentiate it with respect to x, and you get 3y squared. Remember, because 3y squared is like a constant multiplied by x. So x goes away. You know, just like when you take the derivative of 5x, it just becomes 5 and x gets dropped. And then the next one, it's negative sine of 2x plus y. But then you have to multiply this thing by the derivative of the inside function with respect to x, which is 2. Okay, so that's how you can get that. You want to go on to the next problem? No, wait. Okay, so anytime you do problems like this, you know, you want to just stop and smell the roses, or just think about what you have observed. Okay, did you notice that these are the same? Yeah, it's interesting, right? And of course, you may just be able to figure out, maybe it's true all the time. Maybe you can try a few other exercises, and you may want to compare fxy and fyx. And maybe you can do that, maybe 3,000 different examples, and then you find out that's always true. And therefore, it's always true. No, it doesn't work that way in mathematics, okay? No matter how many times you try this, by having hundreds of examples where f of xy is equal to f of yx, that doesn't give you a complete proof, right? So in order to show that this is always true, if that is indeed the case, you have to have a theorem. And theorem requires more general proof. Somebody did that for us, okay? And it's a Frenchman. And so his name is, I'm not going to pronounce it correctly. It's something like Clairaut's theorem. The French people pronounce their R in a way that I can't possibly pronounce. It's like Clairaut's theorem. I don't know how you pronounce it. But his theorem actually proves that these are always, or almost always equal to each other, right? So if fxy and fyx are both continuous. Now this is a technical requirement, because for almost all functions we study, f of xy and f of yx, if they exist, they are almost always continuous. Okay, as long as they're continuous, then fxy is always equal to fyx. And for all practical purposes, for our functions that we will be studying in calculus, or all of your calculus sequence, this will hold. Okay, you will have to have very bizarre, almost twisted-minded kind of a counter examples to show a function that for which this is not true. Okay, so this is going to apply to almost all our functions, and you can try this with different functions for you. All right, just a few more things. If you have a function of 3 variables, so this time it's f, a function, f is, has 3 variables, x, y, and z, and you can call it maybe w or something, In fact, let's go ahead and do this. If w, which is a function of x, y, z is given, then what can you do? You can talk about fx, fy, and fz, right? You can take the partials like fxy, fyz, fxz, and so on. You can exist, or they can exist, in fact, mostly likely exist, and f of xz will be, not surprisingly, f of gx. And by the way, you can do three, the third derivative, like mixed third derivatives, like f of xyz. That's going to be the same as f of z xy, which is equal to, and you can write all six permutations of this. Okay, so these will be a generalized versions of the Clairaut's theorem, or however you pronounce that name. Okay, so let me give you an example here, or in fact, go ahead and practice this on your own. Maybe you can pause this just a second and see if you can you can come up with this. All right, so I will just ask you to do this. Find f x y, f y z, and f of x z. in here. And maybe you can try something else. Maybe you can do f of yx, f of, let's try x, y, z. I'm just creating a bunch of problems here. What's that? Z, y, x. Okay, try that. All right. Let's see if we can do these things here. And of course, the first thing you have to do is to find fx and fy, all right? And I will stop the recording here so we can go to the third section of this, which will be rather short.